Alright, welcome back. Tonight we've got section 9-1. We're going to wrap up the section right now as we look at an application using radian measure, something that you can use in real life. So why we might use radians instead of degrees, for example. Okay, and that idea is linear and angular speed. These are two ideas that relate to an object as it moves about a circular path. So you can think about things that travel in a circle. Maybe it's a like some kind of like spinning roller coaster. It could be a tool that spins around some type of drill, those type of things. All right? So the first idea we'll look at is angular speed. Angular speed is the speed of rotation. The speed of rotation. What that really means is how fast is the object spinning. So we're really not talking about how fast is it moving, like along its path, but how fast is it spinning about that point. You can think about it as, you know, how many degrees or radians or revolutions is it is it making within a particular time. So when you do this, your label is always going to be in some form of degrees, or not degrees necessarily, but some measurement for an angle. So it might be in degrees, it could be in radians, could be in revolutions, anything that you could measure an angle in. So even though I have degrees written there, some measure of degrees, what I really mean it's going to be in some measure of how we measure angles per time. And you can find that just simply by taking theta, so however many however many radians or however far the object has revolved, divided by how much time it took. Now when you're doing angular speed, it's real important that you do make sure that theta is in radians. It's important as we use this with linear speed that we make it in radians. You can have angular speed be labeled in anything, but when you use this with linear speed, it's real important that your theta is in radian measure. So just a simple example. Suppose the object travels 4 pi. So what's that mean? Goes around the circle twice, 2 revolutions, takes 3 seconds to do it. So the speed of that would be 4 pi over 3 radians per second. Just remember, angular speed is how fast the object is spinning. Now, linear speed talks about how fast an object is moving along its circular path. Now that speed needs to be a constant. You know, this formula I'm going to give you isn't going to work for an object that is speeding up or slowing down, but one that is constantly moving along a path. Maybe like you could think of it like a belt. If you have like a pulley system or something like that, as the object moves about that circular path, how fast is it moving? So we're not talking about how fast is it spinning around now, just how fast is that belt moving, if you will. So a formula you can use for that is that that speed. Remember that speed is always just a rate. You know, how fast over how much time. You know, you've learned even when you were younger that speed is just distance divided by time. So we apply that now to the linear idea, the linear speed idea, and that S in that definition above, that speed or that distance divided by how much time is going to be our linear speed. We can find that distance by doing the radius of the object, times the number of radians that it's passing within a certain amount of time. Let me say it one more time here, then I'll kind of unfreeze this video here. That speed is found by taking the radius of the circular object and multiplying it by how many radians the object has covered in a certain amount of time. Think about that in terms of like a circumference idea, and the distance around a circle. Think about how that might compare a little bit if you're trying to get your brain wrapped around that idea there. So again, just to reiterate that notation on there, how many radians that you've covered of a circle with a certain radius over the span of a certain amount of time. So make sure you get that formula squared away in your mind. So let's look at a couple of examples here, and these examples are in your text. So if you want to follow along with that as well as you can. First one's going to be on page 571. We're looking at example number 7. I'm going to read it to you right now in case you don't have your book open right now. It says the blades of a wind turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. So the first question we're going to look at is how do you find the angular speed of the propeller? So remember, angular speed is going to be theta divided by t. And if we're going to label this in radians per minute right now, one revolution, one time around the circle, that's 2 pi. It's got 15 revolutions in a minute, so 15 times 2 pi is going to give us 30 pi. And that's our answer. 30 pi radians per minute. That's our angular speed. So how many radians does it cover over a certain amount of time? Now we can use that now for the linear speed. If you want to find the linear speed, if you're on the tip or the outer edge of the blade, how fast would you be moving around that circular path? So now we got to take into account now how long are those blades. We've got our theta already in radians, so 30 pi. We're going to multiply that by our radius, which is 116 feet. That feet's important. That will help you determine what our label is. And it does that every minute, every single minute. So you multiply that out. Approximate answer here is about 10,933. Again, now what's our label? Go back. What was the radius in? Radius was in feet. What was our time in? Time was in minutes. So we put a label on that. It's 10,933 feet per minute. Again, if you need to stop this, rewind this a couple times, go through that, make sense of that, you should. Alright, one more example. This one's on page 574, question 109. Talking about a car moving down the road. The car is traveling at a rate of 65 miles per hour, and the diameter of its wheels is 2 feet. So part A, what we're going to look at here is find the number of revolutions per minute the wheels are rotating. So how fast are they spinning around? So again, it's an angular speed problem. Alright, revolutions per minute though is what our label is going to be. So we want to know our diameter. Diameter is 2 feet. Half of that is a radius of 1. So to figure this out right now, 65 miles per hour. And really, this is just a conversion problem, really. We're going to take that 65 and multiply it by 5,280. That's the number of feet in a mile. Divide that by 60, which is the number of minutes in an hour. And now you have an angular speed, really, in feet per minute. 5,720 feet per minute. Now, how do you convert that into revolutions per minute? Remember, the circumference is pi times the diameter, or 2 pi r. So there are 2 pi feet in one circumference. So 5,720 divided by that 2 pi will tell you how many times we went around the circle, how many circumferences we have there. And when you work that out, you get just over 910 revolutions per minute. Again, pause this, make sense of that, make sure you understand what we're saying right now. Alright, so now we're going to move on to the next question. Next question is just find the angular speed in radians per minute. And really, this is just a different label for this problem. If we know what the angular speed is in revolutions per minute, how many radians do you have in one revolution? Be 2 pi, right? So what you could do is you could actually just multiply the 910.4 by 2 pi, or realize that we had this answer already earlier. 5,720 radians per minute. It was actually in feet per minute earlier, but because of the radius of the circle being 1 foot, the feet per minute and the radians per minute is exactly the same. It won't always work out that way, but it does if the radius of the circle is 1. Now, why is that important? It's important because if we have our answer in radians per minute, we could use that to answer a linear speed problem as well. Hey, before you come in tomorrow, use the information you have here to answer this last question. Suppose you're a bug and you're stuck on the edge of the wheel. You got ran over, and now you're on the very outside edge of the wheel of the car going down the road. How much distance would you travel in 45 minutes? It's really not a linear speed problem, but an application of what we're doing here. Alright, hope this makes sense. Again, jot down some ideas that maybe were confusing to you, and we'll start class tomorrow with that discussion. If you have questions tonight, you can always get on Facebook, post those. I'll do my best to give you a clear answer before tomorrow. Alright, see ya.